Sir, very good evening. Shantanu Bhattacharya, sir.
Yeah. Good evening, sir. So I'm audible, right?
Yeah. Am I audible, sir?
Yes, you are audible.
Yes, sir. Faculties are joining, sir. We'll take another 2 to 3 minutes. Sharp 7:02 or 7:03 will start the program, sir.
Okay, sir.
Please, sir. Satish, shall we go ahead? Okay. Very good evening to one and all present here. And I welcome the resource person for this session, Shantanu Bhattacharjee, Senior Materials R&D Engineer, Tavastu. And specifically, this topic for this session for today, it is on 3D concrete printing. And before to go ahead, I think people know much on what do you say 3D printed concrete building in IIT Madras. The startup which has done it is Tavastu, and we have got a resource person from the same area. And a bit of an intro of the person. Shantanu Bhattacharya obtained his PhD and MTech from Indian Institute of Technology Madras and BTech from National Institute of Technology Durgapur in civil engineering. He is currently serving as a senior R&D materials engineer at Tavasta Manufacturing Private Limited, a startup leading to the frontiers of 3D printing of concrete structures in India. and they are the peoples who have brought the 3D printing technology to India. During his PhD at IIT Madras in Building Technology and Construction Management Division, he was a recipient of the Prime Minister Research Fellowship. He is a member of the working group CED 32, that is BS code for 3D printing of concrete, and Relim Technical Committee, additive manufacturing in construction. He is interested in additive manufacturing with concrete, special concretes, rheology, cement chemistry, and microstructure, concrete mixtures, and sustainable alternate binder systems. Sir, the session is yours. You can proceed on. Thank you, sir.
Thank
Thanks
you.
for
Thank you.
accepting our invitation to be the resource person for this session.
Thank you. It's my pleasure. So I hope that my screen is visible and I'm audible.
Yeah. Your screen,
Yeah.
we could see that the front screen, that is first page of the screen, is visible, sir.
Thank
And
you.
it's audible too.
So we'll talk about introduction to 3D concrete printing, and this is a basic. It will be a very basic lecture which talks about how additive construction or additive manufacturing is a part of construction, and then we'll talk a bit technical about the things which are important for concrete to be printed. So first we'll start with a very old era of how the construction has actually developed through the development of the construction technology from before Christ or BCE or to present time. So we had beautiful monuments all over India, and like we had Ajanta caves, we had the stupas in Sarnath or Sanchi. Then we have internationally we have structures like Great Pyramid of Giza. All these structures were a part of two different kind of manufacturing. So if we go for the Ajanta caves, it was done through something called subtractive manufacturing, where you have a rock piece, you carve out it, and you make homes or you make caves where the person can live, they can have their dwellings. Then comes the era of stupa, where the people or the Great Pyramids, where the people used to take blocks, and each blocks was stacked one over another to form the whole structure. This is nothing but the starting of additive manufacturing. So the main concept which differs from the Ajanta caves to Sarnath or Great Pyramid of Giza is that in Ajanta caves you have to get the materials out from the cave. So in Ajanta caves we can also compare with something that present in Tamil Nadu, the caves in Mahabalipuram. The same kind of things where it has been the stones have been carved out and the sculptures were made. Then come a very interesting questions that how these great structures were constructed at a time when there was no machines or no like there's very less energy. So there were different methods that have been taken, and you will be very interested to know that the scaffoldings, the formworks, and the way the ropes and the pulley systems have been being worked for now for RCC or normal construction method was still existing when the pyramids were constructed. So basically, the core or the stones and the formwork system is still the same in the practice what was there when the pyramids were made. Then we'll show some interesting things like the structural system changed when we went towards having arches, where we had the you can see the brick arches, the brick masonry constructions, where RCC was not still a part, and we still used to make good mansions, good houses with only bricks and the blocks using geometry and structural engineering as a part of it. And then we came to the era of modern frame structures, where we started making beams, slabs, columns, and RCC, and then the whole construction scenario changed. Now we could make taller houses, wider houses, bigger houses using the modern frame structure. But still, one thing remained the same. What was there at the time of ancient pyramid of Giza is still the same. We still had the formworks, we still had the scaffoldings, and nothing changed the way the construction used to happen. No, I'm not telling that the machines were new that came to construction. There was new ways to do construction. But the scaffoldings, the formwork system, the basic skeleton was exactly the same. And there comes the most interesting part. How much formwork is actually needed for construction? So the formworks that we make, interestingly, we have 20% of the total cost goes for formwork material cost, and 34% of the total construction cost goes for formwork labor cost. 46% is only for the concrete, rebar, footing, placements of concrete and all these things. So the total cost of 54% is taken for normal construction for only formwork material cost and formwork labor cost. And one thing that we can't count with this is the time. So you need 1 day or 2 days or 3 days man days to create this scaffoldings, to create these formworks, and then another 2-3 days to remove the whole thing after the concrete gets set. So the stripping of the formwork again take a longer time and a longer labor intensive work. For removing that, some of the technologies came into play. The one is conventional shuttering, has been moved to Maivan or Mivan technology, where you have the whole shuttering together and then you just put concrete inside it. And then again, that's how the conventional system has been changed a bit to another formwork system that can work good. But there is a chance where 3D printing gets in. 3D printing talks about no formwork construction. That means while having the structural systems integrated into the building itself, we want to move away where you need formwork, scaffoldings to actually construct. Might be 100% removal or even 80 to 90% removal of the total formwork and scaffoldings while the construction is happening in situ and not precast only. So there's a difference. In the precast, you can say, okay, precast is there. You just have to move the molds and put it there. But for 3D printing, we don't need that. So we'll glimpse a small talk about what is automation in construction. So I hope my this animation is visible there.
Yes, sir, visible, sir.
Yeah. So this is the next era of construction. So when we talk about TWSTA, when we talk about BTCM or Building Technology and Construction Management of IIT Madras, what we are actually looking at is changing the construction scenario. That is something that's not been worked upon for a long time, and how disruptive the industry can be. And how interesting it can be for the people who are like, okay, civil is the same old boring stuff. No, we are not in the same old boring stuff. We are trying to make our construction smarter, faster, efficient, and use a lot of modern technologies. Something like autonomous machines, like drones, or a truck which can move through, like you can have a backhoe which can directly take the material and put it in the truck without having any manual intervention. You can have it monitored through 3D laser scanner and stereo camera. Then drones for surveying, that's being used by a lot of people, and professors in IIT Madras like Professor Koshi Verghese and other people are already have done a lot of work on that. Then integrating IoT sensors for the machine to increase the safety of the workers. Then we have virtual reality, which again gets in when we are doing for project planning and training. And the end comes 3D printing. And how it is together, how can we talk about it? I'll go to a very famous photo by BCG analysis. It talks about what the future holds for construction. So this is what we have. We start the life cycle from planning to operations, and what we have is basically 1, 2, 3, 4 major things which are going to change the construction forever. One is the user interfaces and applications. So we have been talking about big data and analytics, simulation and virtual reality, mobility versus an augmented reality. All these things are in labs and somewhere in practice. And again, these all things come where the users can see the buildings better without having constructing them. Then we have BIM and ubiquitous connectivity and tracking systems that help us to track or manage the things. Then comes the next most important part, that is the digital and physical integration layer. So for making a car, you have robots. For making even textile, you have robots. But for construction, you don't have robots. Where the additive manufacturing actually gets in, where the 3D printing actually gets in, it's also called additive manufacturing in other terms. is the robots are getting in construction, and we are integrating a lot of software systems, a lot of high-tech ends to create the houses. So intelligent construction robotics with sensors and all these things are getting added. So this was just a starting introduction that how concrete 3D printing developed and why it is important. Now I will just talk about what is concrete 3D printing and what we have done, and then we'll go for some material related technical stuff. So first is a simple thing, a difference between additive manufacturing and subtractive manufacturing that I was saying. In subtractive manufacturing, you take a material, you subtract it, and you then create an object. In additive, you take the binder system, you add it together, and you create a sub object. So the main thing is that the waste can be reduced a lot. So you will say, okay, like this is being done in civil industry for a long time, correct? For blocks, we have been doing it for blocks, for bricks, for other things for a long time with using molds. And there comes the change. So how the concrete 3D printing happens is that we have a robot which is running and creating layer by layer construction of wall systems, of columns, of walls, of systems, and you don't need a formwork at all, and it will come up together. So it's how the actual printing happens. So it's a primitive one. When we started with, we have this kind of printers, and then there are four main parameters which becomes critical for governing the 3D printing. So 3D printing is like a micro factory. So you have the automation or automatic control of the robotics machine which runs through the things. You have pumpability or a pumping system which needs to pump the material to the hopper or to the auger system. You need to extrude it, like the extrusion system that has been used for bricks manufacturing, for cold bricks and all these things. So you have to extrude it, and then it needs to build in that fresh state to enough height that it doesn't collapse or doesn't bulk out or bulge out. There comes the most interesting part. We have been habituated to create self-compacting concrete. We have been habituated to create pumping concrete, but always we have formwork. We put the concrete in the formwork, we forget about it, we come after 1 day for a column or 7 days for other things, we just strip the formwork out and our concrete is ready inside. The mold was there. But here, the concrete has to stand from the day zero, like this, from the hour zero. The moment it starts printing, it has to stand there and it cannot collapse. That's where the change actually starts. So how does this happen? So there are different other forms of 3D printing also. This is called smart dynamic casting, where again you have a mold and the concrete has to stand on its own on the column while it is getting printed. There is another quite famous approach is called mesh mold printing, where you create the reinforcement using the robots and then you shotcrete the concrete inside like a ferro concrete or ferro cement, and then a robot will come and do the final finishing. Out of all this thing, extrusion based system, that is this system is the most famous and is being used for large scale productions where others are still in the lab scale. So we come to what exactly being printed. So 3D printed structures. So this is the first 3D printed house of India, the first finished 3D printed house, which is in IIT Madras. It was done in 21 days. And it was more like a students and a startup project where people were not equipped enough. So now we can have this in 7 to 8 days. We can have this scale of construction done. So it was done in off-site, in factories, printed and moved to the site, and it has been assembled and the finishing was done. Similarly, L&T has also constructed 2 houses in Kanchipuram using 3D printing. The only thing is that the technology that Twasta has is completely made in India, from robots to the material to the machine and everything. In world also, there's a lot of thing going on 3D printing. You can see we are having columns, beautiful columns, small culverts, bridges, and then houses in Netherlands, and then WASP is making with clay that they want to print, and they are printing with it to create sustainable eco structures where people can live. In ETS Zurich, people have printed a whole house called DFAB house using 3D printed elements with walls, with roofs, with slab and everything. So each of the component can be printed with 3D printing without having any issue. What exactly more can be done? So I will show you 3 structures that have been printed by Twasta. In the left, you can see the Anant Siras that was inaugurated by Honorable Home Minister. So you can see that it's a completely twisted tower, which is 2-story in height. It's almost 6 to 7 meters in height, and it has 4 twisted things, and there is no single rod running in the middle. It looks like a DNA, a helical structure with 4 things being twisted. This is something that 3D printing can do. It is very hard to do with the conventional construction. You see the bus stop here, the Godrej bus stop. You see this beautiful curvature that is done. So it was done with 3D printing. 4 models were printed. They were stacked together on site, and the print and it was finished in within 10 to 15 days of starting of the project. You can see that this kind of curves and all these things with cement, with concrete to be done, you need a huge mold system. And for 3D printing, you don't need anything. You just can print it within 1 day. We can print one full 1/4 of the module, and if we have larger printing systems, we can print the whole structure in 1 day. So how big we can print? That's the question is. So question will be that, okay, there are machines, and you are saying small modules. How big we can print? Can we print houses on site? So if you come here, you will see this is the printer that Twasta has in Chennai itself, near a facility near Maraimalai Nagar. This is the people's, you can see the people here, like the human beings here. And this is a printer that can print up to 10 meters. So a 10-meter height building can be constructed continuously. We have smaller printers which can print up to a 1-story houses, a 2-story houses. Then we have robotic arms that can print with the polar coordination. Apart from that, the scale of printing that is possible is enormous. So even L&T is working on creating a G+2 structure, a G+1 structure. We are working with IIT Madras to create the first G+1 structure in IIT Madras, which will be architecturally, which will have off-site and on-site both construction together. There's a lot of like you can construct very fast with this technology. So now I will go a bit towards the technical terms and understandings of how this 3D printing works. So here I am showing you 2 different photos. This is a gantry system with rails in it. The rails can move. So you have a pump system and an RMC truck or a normal truck with 3D printed concrete. It can pour it directly into the pump, and it can push the material up to the nozzle, and the nozzle, you can print it and you can create the whole house. This is a crane system where you have a boom and a crane where again you can print it around the circle. It works more like a crane, which you have been seeing for normal construction to lift weights and all these things. Instead of that, we can print with that. So if you go a bit detailed, we can break the whole component into 9 major parts. The first is obviously the computer, which you need to design the tool path and generate the G code. At this moment, generating G code has become much easier because of the open access, and now tools are also there, but open access codes are there, whether you can give a CAD file, a CAD or CAD file, it will convert into a .stl file, and then the softwares also are present in both, like the companies which are making robots like Twasta or Mica or other people, they are also making the softwares, or there are open source softwares where you have to give you a CAD file and they will make the printable model, that is a STL file, .stl file that it will be converted to. It's very easy to do it now. Next is the robot controller for reading the generated code and controlling the robots. Here comes the main part, where this G code and the robot is integrated, and this is what we call the physical and cyber integration. So whatever drawing the CAD files or BIM or whatever you have been doing in computer, the same thing the robot can actually do while printing itself. So any structure, any shape can be printed through. The third thing is this extrusion nozzle. That is very important. The robot for moving extrusion nozzle. That is very important because again, we have robotic arms, we have gantry systems, and it has to have a minimum capacity to move here and there and have the printing. The fourth thing that comes is the ink or the mix. That is important, and for that you need a mixer system. You need it to pump through your pumping system, and then you need the pump to be controlled from the software. That the material also gets up to this point, and this needs to be extruded into the extruder, and then the printing has to be done. So the ink itself has to be different from whatever concrete we are habituated with. with pumpable concrete, whatever IS code, IS 456 says, or whatever even the new IS code says. We can't move with this concrete, and that's why we have a new kind of concrete in the field, which is called a printable concrete, a 3D printable concrete. We are working on the BIS code or the IS code, that is commonly known as, so that we can create a guideline so people can actually print it, the people can actually test it, and they can use that guideline to have a minimal understanding of the 3D printing. When we go further into the system, that how does a CAD model or a model gets distributed so that it can actually be printed. So when we give a CAD file, three things we have to be done. One is that the FEM analysis or structural analysis has to be done to find out whether the structure is stable or not. Then we integrate that with the BIM model or building information modeling, and then we have the material designs and properties that has to be fed in. Based on that, what we create is a topological analysis, or what we create is a file that can be further exported as a STL file. The slicing is done, and then slicing is nothing but you have once you have a circle or a cylinder, the printer needs it as slices. So it basically extrudes, in the sense it creates a 2D model and it will keep on going in the third dimension. And third dimension doesn't need to be a straight one, it can be any angle and any turns and any curves. So the slicing is done, and then each slice is converted into a G code, which again we need to have some data analysis and optimization processes. From that, we go for the creating or the printing the whole structure, and the concrete printer is controlled. That's how it works. So when we go further, and when we talk about digital concrete or digital construction, it's not limited to only extrusion-based 3D printing on this thing. So we divide it into two things. One is no formworks and non-conventional formwork systems. In no formworks, we again have the same thing. We do the contour crafting or these things. Then we have some people who have been working with something called stay-in-place formwork, where you print a polythene formwork outside or something like that, and you fill the concrete inside, and then you just remove the formwork. And the formwork can come out like a eggshell. So we are not talking about that. It's just for a glimpse that is also available. Now we'll go a bit deep into the material science. So how does the material science, or what do you understand with the material parameters that are important? The first thing is that how does the printed elements or element, when it is being printed, fails? There are two basic mechanisms behind this. One is your buckling or elastic buckling or buckling. We don't use elastic plastic, but we generally consider it as elastic buckling, and we are doing a calculation as per that. Then we have the plastic collapse of the structure, where the layers will break and the whole structure will fall. So you can see this. This is the very initially when we print something, and there are cases where it just fell down. So you can see that it buckled out, or it fell down. This is another failing where you print it continuously, and you can see that there is small deviations happening, and this is how again the bulging or the buckling in happens. So here you have to understand two things, that a printing structure needs to actually print properly so that it can hold there, and it should not fail like this. So there are two basic mechanics or mechanism that comes: elastic buckling, plastic collapse. In plastic collapse, you can see that the lower layers sometimes get compressed too much, and the whole structure becomes like a trapezoid because the lower layers are getting compressed and it is failing out. Then the structure falls like this and it just collapses. So the whole material science that we talk about talks about how can we actually allow the printing without having any kind of collapse. This is where the collapse happens. So for that, we'll go deep into that, like how to actually have it in the fresh state when it is being printed so that it doesn't collapse. But before that, we have to understand there are a few parameters that are very important that influence the 3D printed concrete's behavior. The first is the mixed design. We call it a multi-level material design, and it's being quite widely used by people. So the SCM, the VEA, superplasticizer, and different kind of chemicals are used. Different kind of mineral admixtures and chemical admixtures are used to get the rheological behavior. Again, rheological behavior doesn't mean that you need a rheometer. Rheological behavior can also be easily examined using a slump, using a flow table, using a compactor or anything. Then you have to understand the delivery and placement and tribology. Again, tribology is something that goes in how the layer. So when you push the concrete through the pipe, a layer forms on between the concrete and the pipe that actually helps the concrete to move forward. This layer is the main thing that actually helps the concrete to get pumped. When my concrete is like an SCC, I don't have any problem because it always moves like a water. But when I have a stiff concrete that is required for 3D printing, I have only the layer which is surrounding the material and the pipe, so which can actually do that. So if I actually make it, so if this is the pipe and I have a concrete going through inside, concrete material, so this zone is where the tribology comes into play. So tribology becomes important for this thing. So this behavior is what governs the pumping of the material. Now, how to study that? The most of the rheological tests that have been done, the tau, the shear yield stress, and the mu values that we find out, that actually works to find out how this layer, which we also call lubricating layer, because it lubricates or flows the material, how it works. And we have some relation for that. Now, it's not like that if you don't have a rheometer, you can't make a 3D printable concrete. Believe me, we have been working when 3D printed concrete without having any concrete rheometer as such. We go with the basic tests. Again, the test like slump, flow, flow table and all these things, and we find out the parameters that are critical to have this pumping and all these things. Now we have the other thing that is important is the pumpability and buildability, then mechanical properties, and how to integrate reinforcements. There are these three things again being controlled by how well we are packing the aggregate. So when you make a concrete mix design, there are two ways to do it. One is that you follow the existing guidelines, existing codes, and you make this mix with that. This much will be the aggregate binder ratio, this much will be the coarse aggregate, this much will be the fine aggregate, this much will be the water binder ratio, you make it. The other approach is called the particle packing approach. And what happens in particle packing approach? You basically try to have all the dry materials together and you create a sieve analysis, that particle passing graph, and you plot it to create a S curve. So if you remember, obviously you are working with it every day. So we have to create a S curve. A S curve gives a perfect packing. That's what we call like well-graded materials, uniformly graded materials. So we always try to have a well-graded materials, well-graded sand. That is better for us. So this particle packing is very important, and the most better particle packing we have, we can go with the lesser water to binder ratio. And with that, we can actually gain a good strength, and we can also get the other properties. So packing becomes a very critical thing. So designing by packing or particle packing is the way how the concrete design should be, how the concrete design in future should look like. And it has to be, there are very few softwares there like EMA and other things, and this can also be done manually to just do how we do that fine aggregate or coarse aggregate, and together we create an all-in aggregate iteration. The same way everything can be mashed together. Then other thing that is important is the fiber. Fibers are very important for 3D printing in terms of plastic shrinkage. What happens is that since we print it and it is being exposed to atmosphere from the 0th minute, that is the moment we print it, it is exposed to atmosphere, it is exposed to heat, sunlight and drying. We need enough fiber so that it doesn't crack under plastic shrinkage and drying shrinkage. So it's very important that we incorporate fiber systems inside. All this thing again comes to a term called thixotropy, which is again being affected by the packing and the fiber density both. Thixotropy, the behavior what clays give. That is, once you put it into shear, you breaks the chain, it again rebuilds back, and it can hold its place. So the thixotropy again controls all the three behaviors of buildability, pumpability, and extrudability. And if we get it inside a funnel, what is quite used for conceptual model for mixed design of printable mix, we have rheological properties, which is being again controlled by this basic thing. So that's why I'm saying you don't need a rheometer. If you know how to do packing, if you know how fibers works, and if you know how thixotropic it is, it can be, you can measure the different ways. You can actually make a rheologically proper material that can be printed. Then it is further taken for mechanical analysis and interlayer bonds that I will talk in the coming slides. So how does actually this failure mechanism works? There are two modes of failure. In one, you have the yield stress development. That is the plastic collapse. So what is plastic collapse? When the shear stress that is coming is greater than the yield stress. So material can only stay as a solid until it reaches its yield stress. The moment the yield stress is reached, it starts to behave like a fluid, or it will be a plastic deformation will be there. So even though a hardened concrete, you have a behavior of sigma versus epsilon, like this, in the fresh state of 0 to 30 minutes, a behavior of stress versus strain is like this. This is the plastic region where it is behaving. So beyond or below a particular range, we don't know exactly where the plastic region started. The material will move from the yield stress tau y. When the applied stress is greater than the yield stress, the material will start to behave like a plastic mix. So people have studied that how this shear yield stress or the shear stress develop with time. Can you change the rate of printing so that you don't get a collapse or you don't get a plastic collapse? Then the question comes, how does a single layer deforms? This is how a single layer deforms. So this is what an undeformed layer is when you're printing it. And self-weight or the coming of weight, the layers deform to form a structure like this. And this again can be divided into three parts, which is one is your the unconfined part. Then you have a laterally confined part in the bottom. So what does this mean? That means that here the mechanics of material is different from this region. It's an unconfined case, it's a laterally confined. So here you have sigma x, sigma y, and sigma z, all three actually giving you a compression. Whereas in unconfined, you have only sigma z that is giving you a compression, and there is no sigma x or sigma y. So anyway, when something is being confined from all the three sides, we have a hydrostatic pressure case. In that case, we don't get deformation. So this part won't deform much, but the upper part will deform. And same will be a part here where there will be biaxial stress, that is either sigma y and sigma z will be present, or sigma x and sigma z will be present, which will lead to the deformation in the second part. So the question comes that why is that important? It is important because each layer mechanism is important to understand how we can have a layer without getting deformed. So either if the whole layer is under a triaxial compression, it won't deform, or we have to satisfy the sigma z criteria, and the sigma z should be greater than the yield stress so that we don't end up with having a plastic compression. And how we can control it through the material side, we can either have a physical reflocculation or a chemical hydration. In chemical hydration, you add accelerators and other things that can improve the behavior of the property of hydration, and it will make into a fluid to a solid thing. In the second term, the reflocculation, where a clay kind of behavior happens, where once you mold the clay, it is moldable. When you keep it, it is solid. In that case, the reflocculation happens, and it also helps for increasing the buildability or this shape stabilization of the printed layers. But what happens when we actually print with a lot of different materials or a lot of different time gaps? Time gap is the time difference between two layers that is getting printed. Okay, so this time gap is very important. Why? If we increase the time gap, you can see that there is a very beautiful bond between these two parts. But when you increase this time gap, you get very bad bonding. So you can see these big gaps, right? These gaps form when the two layers, the time between two layers are too much, or the material is having very high elasticity or very rapid setting. So before you can put the next layer, if this layer sets, now you know what is the setting, right? If the layer sets, it becomes a solid. And when the next layer comes, there won't be any proper bonding between them. And then you can see this kind of voids forming. So the bonding, the material again becomes very critical thing. So it's not only that it has to
mask எடுத்து போட்டுக்கோ.
Yeah.
It's somebody else.
Okay. Yeah. So you can see that this layers here are not that bad because being printed continuously, whereas you can get this kind of printing if the time gap is very high, or you have a very fast setting material. So if the one layer sets before the next layer comes, you end up with a wide gap. So that is again a very important thing that we have to, when we as a material people, or when we as structural people or civil people have to design, we have to have a proportion of setting in a way that it doesn't collapse while printing and it doesn't form this kind of gaps. So what do we do, and what the materials that we print with? So it's just a glimpse. You can see how the printing is happening of a column in the right side. So the printer is continuously moving, and your layer is being printed one after another. There will be no collapse, and it will be printed. The materials what we use are very commonly available: OPC, PPC, slag, and then we also use some specialized material for special cases. So this printing is done with limestone calcined clay, which is quite in news, and IIT Madras has done a lot of work on that. There's another sustainable cement that is coming into the market, and we have been doing printing with that also, limestone calcined clay cement. And then there is calcium aluminum sulfate cement, or CSA, which is again a very popular cement in China, but in India we don't have a source. It's a very high quick set, it's a very rapid quick set, hardening cement. So you can get the 28 days strength in one day. One day you can get a strength which is equal to 28 days strength for other places when you use a CS. But unfortunately we don't get it in India much, and it is again for studies also you have to get it from China or Egypt. Then we use different kind of sands. We use normal fine silica sand, quartz sand. We use normal M sand or quartz sand, recycled concrete, quartz aggregate also we have been printing, and you can see that how this printing occurs one after one, and the layers keep on coming. So these are different ways we have printed this 1 meter continuous within your 10 minutes. So we have even printed faster than that. We have printed 1 meter in around some 5 minutes or 6 minutes. So basically you can print a 3 meter continuously in 25 to 30 minutes maximum, with a gap at 1.5 meter, so that the material gets, and you can actually make 3 meter columns continuously within half an hour to 45 minutes. We can again, what we have shown here is that there are some literatures that talk about we have to only use lower aggregate binder ratio, but we have been printing with higher aggregate binder ratio. That is the cement content in this case, it was OPC and LC2. The cement content in this case was only 250, and hardly 400 and 400 around. So this is well within what IS 456 recommends for drying shrinkage. IS 456 recommends that we should have a 450 kg per meter cube less than that cement content, and that we are already in the printing system. So printing system is no more. You cannot say that, oh no, it's a very costly, it's a non-sustainable thing. No, it's not. We have been working on this for a long time. In IIT we had 2 PhDs and Professor Manu Santanam, I am also student. We have been working on this. Then there are Dr. Smati and other things who are also working with us, other people, and we have been creating mixes that we have come down to having binder content less or equal to whatever is available for a normal concrete, normal OPC systems, with a strength where we're talking about around M40 grade concrete here. So whatever we're talking about is M40 grade concrete, and in sustainability again we have been doing analysis, and we have been trying to reduce it further and further down, where we have already been cutting it to around 60% of what a normal concrete holds, and then you have volumetric reduction also that is there. So what is the future? What are we talking about? Whatever we have been talking about till now was more into the material science aspect of 3D printing, the aspect of structures. Before I go for the future of 3D printing, I want to talk 2 to 3 things that still bothers us, that is still open for research and still open for understanding. The one thing that we are now doing is something which called mechanical testing of the 3D printing and trying to create a code out of it, the IS code, which will give you a specification, some guidelines to do the testings. Same time, there is a committee called RILEM, which is from Europe as the basis, and it's an international committee where we also work. And there's a study going between all the labs in the world to find out how to say that how to test a concrete which is 3D printed, and what are the different values that we can get, how much scatter which we can get. So the Gaussian curve that you remember that you use for the normal concrete, is it even possible to use that or not? And a lot of research is going on there. And with mechanical, there comes the durability properties that are very critical, and a lot of research is going on that. So how to find the water absorption, water swing, and shrinkage values, and all these things. But that's not the end. We are not talking about only printing in earth. What we are talking is interest. So we can actually print in all over the, like we can print in moon, we can print in Mars, and that concept is being there and is being followed for in NASA, in ISRO, in eminent institutes and the centers which are working on 3D printing. So can we actually do robotic 3D printing at places where we cannot send people to construct? That can be somewhere in Ladakh, that can be some mountainous area where there are no labors, that can be an arid region or desert, a place in the center of the village where there is no other facility where a robot can construct. And then it can be Mars, it can be moon, and it can be anywhere. So these are some concepts that has been developed, and people are working on creating lunar concrete, Mars concrete, which can work on that. And then there comes, this is a concept which is going to be there in future, maybe may not be even 10 years, maybe even less than that, when we will start actually constructing on moon for the astronauts to go and stay and create a habitable community. Already directly there, they will take the regolith or the soil that you see here, and they will make some proportions and binders out of it, and they will construct a house in moon. So there's a small glimpse on 3D printing and what it was and how it would be. And now I say I have taken some half an hour for question and answer. So if there's any doubt, I can answer that.
Yes, sir. It's a nice presentation, sir. We had very good ideas on 3D concrete printing.
Yeah.
And I think there will be a lot number of questions, sir. We'll wait. Faculty, it is open. You can either type in the chat box.
Yeah, please.
So, such I have got a question. So the
Yes.
maximum I think you said is M14, sir. Other than that, also can we make it?
Yes, sir. Like we are already working to create M70 to M100 concrete.
Okay.
In the lowest, it is already there. M50, M20 we have been doing. So we are already getting M70 to M80 level of things.
So some person has asked, it is Venkatesh Sagar.
For construction of okay. The cost is something. So like we have to understand two things here. What we are doing is we cannot compare a concrete structure with a brick structure. So if we have a similar kind of concrete blocks that we have, so solid blocks that is quite the hollow solid blocks that is quite available in market nowadays, we can have the same construction being done, and the cost will be hardly 10% more, 15% more. But once you do it in a large scale, or once you do it in a row housing or apartment housing, you cut down almost 60% of the labor cost and almost increase the efficiency by 300 times. So you can actually make one house in 7 days and move forward. So you can actually cut the total cost out there, and it's a micro factory. So you don't have to need huge RNC trucks to come there. You can just have small batch mixer systems, and you can take on printing, and it can work for 24 hours continuously. So it's a large scale structure systems or a complicated shapes where you need a very unique shape or unique architectural shapes. There it becomes almost 20 to 30% profitable than a normal construction. For a house, you will have a normal house, you will have just a breakover point. That's it.
And in your presentation, I think you mentioned about reinforcements. I think it is the fiber which you use it. You say it as a reinforcement. Or specific any other
We
reinforcement you
have
go
steel
ahead.
reinforcements also. So
Okay.
the steel reinforcement are integrated with the printing system, and we have steel TMT bars as the reinforcements. We have grouted concrete also, and
But
then
construction process will differ, na, sir, for that one.
no. So what happens is that we print. So suppose we are printing the wall system, we print the wall. We have hollow portions there, so we can create continuously 3-meter walls, and we can put the rebars inside and put the grout there.
Okay. Okay.
And the grout doesn't need to take the strength for the next day printing, because the wall that you have printed is actually taking the next day strength. So you can keep on printing over that.
Okay.
So the walls become a load bearing structures, and the printed part mostly act as a cover concrete, or it also like the reinforced part is the main load bearing structure, and then you have normal cover concrete. So it's mostly the same system that you use for a conventional concrete. Yeah, so slab is, so there are two things. One is that we still go for a precast slab because it's cheaper for us to make it, because once you have it there, you can just put it when you have a 3D printed house. But we are also working on 3D printing the slab with the minimum number of support system in the base. So we want to cut down the props, that the straight vertical props that are there, from around, if we are using 100% today, we want to make it 30%. We are already working on that, and do the slab printing while we are with the robots there only. So that's still in the research, and that's still being doing. We have a project with SCRC. We might be working on that with SCRC in that case. CSR. Yeah. So in Moon, which material will used? Okay. So when you are constructing in Moon, the main material that is being will be used will be the soil of the Moon. The soil is called regolith. That's what we call for any soil that is not for Earth. So the top soil, what we call this humus top soil, that is same to that. It's called regolith, and that has to be. So there are different ways to do that. It can be sintered, or it can be mixed with some other binders. And interestingly, we cannot use water there, because we don't have so much water in Moon. Might be in the other side, the far side of the Moon, which we have not still reached properly, but we don't have much water, so we go for waterless concrete, waterless cement systems, and and then we are trying to construct it. So it's still in research. Different groups are working on that. We are also working on that. We are still trying to figure it out. Industrial visit, we can see for that. In 17th and 18th March, there is a conference in IIT Madras for concrete 3D printing. People are welcome to come and join that.
Sir, is there any maximum size of the aggregate that can be utilized in it?
So till now, most of the construction are with the fine aggregates.
No
with the coarse
aggregate has been
aggregate,
used.
So we have not done on the large scale. In lab scale, we have printed with 8mm aggregates, 8 to 10mm aggregates. Now again, it's most like the SCC or UHPC cases, where we have a smaller size of aggregates as the major thing. So 20mm aggregates may not be possible to print with 3D printing, because
sure.
it's not possible to have such a huge system. Like, it will again be a detrimental thing for us. So the total aggregate content won't be much different. Only the size might come down.
Oh, size will reduce.
Yeah. So we are okay with the M sand or a normal sand zones that are present in IS 383. So we keep on printing with that, and then we have to coat aggregate up to 8mm. But again, there is something a demand for the finish or the texture that 3D printing gives. So people love that finish, where if there are aggregates, they don't get that finish. The large aggregates will distort the finish or the smoothness of the structures. So the people want that smoothness, and you don't have to plaster it. You can directly put the primer and paint on that. So the whole plastering cost is zero. You can just put the primer and a paint on that, and a normal primer and normal paint will work.
Moreover, whatever the printing is not going to be a circular diameter.
No. It can be any. It can be any dimension. It doesn't need to be a circular one.
Yeah. The one which you have constructed in IIT Madras is not that one, I think so. Not a
In
circular
ID
one.
Plus, we have circular thing, but we have been doing other things. Like I've shown you that the twisted towers and other things. We can
Yeah,
print
yeah,
in
yeah.
any shape. Any shape
Oh,
we
nice,
can print.
nice, nice, nice.
Go back to the slide. I think. So you can see the structure
Yeah,
there, right? Left side. Yeah. So so this is being printed. So you see each the twisted tower that is being printed together, assembled there, and it was grouted with the rebars inside.
wow,
It is there. If you come to Chennai,
yeah,
India Cement's factory, sorry, office, main office, India Cement's main office. That is, if you come from station towards Adyar or anywhere, you'll just find it on the right side, standing tall there. So it's just visible from the outside, from the road.
nice, sir, nice work.
And again, the bus stand, you can see any shape can be printed. So this can be printed modules, and it can be just it can be
Srinivasan sir,
arranged.
you are raising with your hand. Any questions, sir? Srinivasan sir? And any queries from your participants? Satish, shall we wind it up, ma? Satish? Thank you, sir. Thank you, Shantanu
Thank you.
Bhattacharya, sir, for your nice presentation and a detailed explanation on 3D printing on concrete. It was a very nice session, sir, and as well as a very good, interesting session, sir. Thank you, sir. Thanks for spending your time with us, sir. Thank you.
Thank you.
And Satish, you can leave his mail ID so that any people who would want to contact him can mail him.
Yeah, I will just leave it here. It will be better.
Yes, sir. Please. Thank you. Yeah, please. Feedbacks can be left over here. Session. Mail ID, Satish, I think, hope you have to give them which mail ID to mail them. Right. Yeah, please. Pratap, sir, are you available, sir? Yeah, you can mail your feedbacks to the mail ID is given it. Thank you once again for all the participants because without participant, I think the sessions won't be much interesting too. Because as Satish rightly pointed out, you got a very good number of large crowd as well as both in our G Meet as well as in YouTube link. Thank you. Once again, we will all meet back once again in like sessions like this type of sessions. Thank you all. Satish, anything else? If you want to leave back, you can say them. Yeah, feedback link has been shared. Nagarajan sir, it is available. You can take it there. Feedback link. Yeah, you can send them. Send them to the WhatsApp group so that it will be there for them. Shall we close on the meeting too, ma? Yeah, please. MCQ link also they are asking.